Yeah. So hello everyone. Welcome to the second week of this tutorial session of the course NOC 24MA29 ring theory. So I am Pawan Kumar Raikwade. I will solve some sample problems which will help you to solve the current assignments and understand the concepts better. Okay. So let's start. So question number one. These questions are about homomorphisms and kernels, ideals, maximal ideals, prime ideals, which are the content of this week. Okay. So my first question is a basic question. Prove that the ring 2Z is not isomorphic to 3Z. Basically, 2Z and 3Z are not isomorphic rings. Okay. How do you answer this question? So when do we say the two rings are isomorphic? When there exists a bijective homomorphism between those. Okay, then we say that the two rings are isomorphic. So we say rings R and S are isomorphic if there exists a phi mapping from R to S such that phi is bijective homomorphism. Okay, so now every homomorphism has to be a group homomorphism as well, right? If it is a ring homomorphism, it has to be a group homomorphism also. So a basic calculation will show us that any ring homomorphism from 2Z to 3Z is of the following type. If phi is a mapping from 2Z to 3Z is a group homomorphism, okay, then so let's say alpha is phi of 2, right? Which belongs to 3Z. Okay, then what can you say about any element? Any element, that an element x belongs to 2Z, which implies what there exists n belongs to Z such that x equals to 2 times n. Right? So what is phi of x? We have phi of 2n, which is phi of 2 plus 2 until 2 n times, which is because phi is a group homomorphism. Now I can separate it. This is n times phi of 2, right? So what is n times alpha? Let's see. So any homomorphism will be of this form, right? So when will this be a ring homomorphism? That's the question. Right? And suppose x and y are the two elements in your ring 2Z. What is phi x? Again, instead of writing in this way, how can I write this? This is I can write 2n alpha by 2, which is alpha by 2 times x. Right? This is my homomorphism. Perfect. Yes. So what is my phi x? It is alpha by 2x. And what is my phi y? Phi y is again alpha by 2y. Okay. So now phi of xy because if x and y are element of 2z, xy is again an element of 2z, and how is the map defined? Phi of xy will be alpha by 2 xy. Right? But if I do phi x into phi y, I'll get alpha by 2x into alpha by 2y, which is alpha squared by 4xy. Right? This is equation 1. Let's say this is equation 2. Then from 1 and 2, I get alpha by 2 xy is same as alpha squared by 4xy. But when is this true? I can take x and y non-zero, right? This will imply alpha by 2 is same as alpha squared by 4, which is true if and only if I get alpha minus alpha squared by 2 is 0. Right? This is happens only if alpha equals to 0 or alpha equals to 2. Right? These are the only cases, right? So, if my calculation is correct, but is this possible? Now, what is alpha? Alpha basically was the image of 2, right? And I got the choices for alpha are 0 or 2. If I put alpha equals to 0, then my phi will be just a 0 mapping, right? It is no longer an isomorphism, right? Bijectivity, we want phi to be a bijective map, right? So alpha cannot be 0 in that case, but if alpha is 2, you are no longer in 3z, right? This is also not possible because you are giving a map from 2z to 3z, right? Hence there doesn't exist any isomorphism from 2z to 3z, ring isomorphism. Okay? Hence these two rings, 2z and 3z, are not isomorphic as rings. Okay. I hope this is clear. The question number 1. Yes. So I just explained that the rings 2z and 3z are not isomorphic as rings, and I explicitly showed that any map phi, if I start from 2z to 3z, that cannot be ring homomorphism and bijective. Okay, I hope this is fine. Am I still audible? Is there any problem in audio?
Yes, sir, audible.
Okay, thank you. Next question is question number 2. Show that z over x is not isomorphic to q over x. Basically, this was a symbol for isomorphism, and when you backslash it, that's a symbol for non-isomorphism. Okay. So if you remember in last session, I have explained that whenever you have R as a ring, then the units in R over X are same as the units in R, right? So if suppose phi from Q over X to Z over X is an isomorphism, then phi of U has to be a unit in Zx for every unit U in Qx, right? Now what are the units in Qx? As you know, units in Qx are same as units in Q. Similarly, units in Zx are same as units in Z, right? Then what can I conclude? If first unit in Qx, let's say the const 1 belongs to Q over X, And we know that under a ring homomorphism, if the codomain is an integral domain, then phi of 1 has to be 1, right? The unity has to go to unity, right? Under a ring isomorphism, if the codomain is a integral domain, right? So now, because your codomain here is Zx is an integral domain, that means phi of 1 is 1. Now take another unit, let's say 2, because 2 is a unit of rationals. You have a multiplicative inverse, right? 1 by 2. Hence 2 is a unit in Q over X. Unit. Hence phi of 2 has to be a unit. What are the choices? Phi of 2 can only go to minus 1. Why? Because the only units in Z are 1 and minus 1, right? 1 is already taken by 1, and phi is an isomorphism, so it's a 1 1 map. Another element cannot go to 1. So phi of 2 can only go to minus 1. Let's suppose phi of 2 also goes to minus 1. Then what are choices for every other, or let's say for 3, phi of 3? See, 3 is also a unit, so phi of 3 also has to be a unit, but there are only 2 units in Z, which are 1 or minus 1, and both are occupied, right, already. So there are no choice for phi of 3, right? Hence, then here you get no. Hence, there doesn't exist any isomorphism phi from Qx to Zx, which implies Qx is not isomorphic to Zx. Okay, I hope there is no problem in this.
Sir,
Okay, thank you. Okay, let's go to the next question. Okay, now the question number 3. Find all homomorphic images of Z. Find all homomorphic images of Z. Okay, answer. Since you know, if uh, phi is a mapping from ring R to S, is a is a ring homomorphism, then kernel phi is an ideal and range of phi. Okay, so how do you write? Range of phi is isomorphic to R quotient kernel phi. Right? This is a one-one relation, right? Under isomorphism. So this is the first theorem of homomorphism, right? So now I want to find the range of phi's, right? I want to find all homomorphic range of Z, right? So it is enough to find all kernels of phi. Whenever you find all kernels of phi, R quotient kernel phi are the ranges, right? So question is basically what are the ideals in Z? It is simple exercise. I'll give it to you. Exercise. Show that ideals in Z are of the following form. Simply are of the type NZ, right? For some n in natural numbers. So now if these are the only ideals, then if suppose phi from Z to any ring R is a homomorphism, then you know what is phi of Z, that is range of phi is Z quotient kernel phi, right? But kernel phi is an ideal, hence it is some nz for any z. And you know what is this? This is Zn, right? So basically homomorphic images of integers are Zn. Okay, you don't have any other rings there. Okay, so find all homomorphic images of Z. The answer is Zn. It's a simple question, so we'll go forward. Next question. Question number 4. Okay, we have decide which of the following ideals, which of the following are ideals of Z over X. This is the abbreviation for which of the following. Okay, polynomials whose constant term is a multiple of 3, let's say. Is this an ideal? Answer. What do you think? Anyone can answer me. Is this an ideal of ZX? So it's a very simple question. You can answer, okay, without any much thinking.
I think no, sir.
Huh? Pardon? I couldn't hear you. Did you say no?
Yes, sir.
Yeah, it's correct. So this is not an ideal. Very easy to prove. You take any polynomial, let's say you take f belongs to I. I mean, whenever you, in whichever case you are in, I call that set as I. Okay, that is the nomenclature I'm deciding. So let f belongs to I. Then you just multiply with constant polynomial. Let's say alpha f. Okay, doesn't belongs to I, because what is alpha f's constant term? Right, this is 3 alpha. Okay, so if alpha is not equal to 1, you have this doesn't, which implies alpha f doesn't belongs to I. Right, because I has the property that f of 0, a constant term for any polynomial is f of 0, right? F of 0 is 3, but what is alpha f at 0? It's 3 times alpha, so it need not be 3 always. So what is b? So polynomial whose constant term, coefficient of x and coefficient of x square are 0. Is this an ideal? Yes. What do you think? Anyone can answer? Okay, so the answer is yes. We take I as what does it mean? A polynomial constant term coefficient of x and x square are 0. It is like of this form. Some a3 x cube plus a4 x raised to x a4 x4 or something like this until some a and x raised to n. Okay, where n is greater equal to 3 of course, and ai's are reals or whatever your field you are taking. Okay, so this is my I. So is it an ideal, right? Okay, not R. You are in Z always. Right? You are in Z. So question is it an ideal? Can I write any polynomial if I take, suppose I take P belongs to I, which implies I can write P of x is, I can take x square common, right, from all these terms. So I can take not x square, x cube times some other polynomial qx, right? What does it mean? This means I is a polynomial generated by x cube. That's all, right? So like basically, if you don't write like this, now let any polynomial q belongs to zx. Then what is q times p, which is simply x cube times q. Okay, I shouldn't write something else. Let's say r. This is simply r times x cube into qx, because product is commutative. I can write this as x cube times r times qx. So simply this again belongs to I, because x square and x terms are not there. Constant term is also not there. Since you are directly multiplying with x cube, they vanish. This will imply I is an ideal. Okay. Now we are at question C. Z over x squared. Okay. What does it mean? This means it has only even terms. Okay. That is set of all px. If I write a0 plus a1x plus a2x squared until a n x raised to n, such that a I are 0 and I is odd. Okay, is this an ideal? That's the question. Okay, what is your intention? Naturally, you can think addition of two elements are again there, so and 0 is there, right? So it's a subring, of course. If you multiply, is it a subring? Yeah, that's the question now. Is it a subring? Because an ideal has to be a subring, right? So uh, let's take two elements. P comma Q belongs to zx squared, right? Okay, so P has only even powers, Q also has only even powers. So if I multiply, yeah, so naturally PQ will also be there, because even when you add, it's again an even, right? Even plus even will give you even number itself. So powers will be even for PQ also. But what if P you take an element R belongs to any polynomial, and you take an element P belongs to zx squared, is RP belongs to zx squared? The answer is no. For example, you take a polynomial P as x squared, simply this belongs to zx squared, and you take x belongs to zx, then what is, you take this as r. What is rp? Is x cube, right? Which is no longer in I. What is your I? I is zx squared. So that's all, simple. Not an ideal. It's suffering, but not an ideal. Okay, you okay, Hariram Singh, you have a problem with last question? See, what is the definition of an ideal? It means if you take an element from that set and you multiply it with any
Sir,
element from the yes,
A number.
this one.
Yes, sir.
See, a polynomial is constant term is a multiple of 3. This is your set, right? I set of all polynomials is constant term is 3. Okay. So suppose
Yes, sir.
you take f from I, that means its constant term is 3. For example, if suppose f is like this, fx equals to x plus 3. Okay, this is a polynomial.
Yes, sir.
I. Suppose I multiply this with a constant I. R should be in zx, right? If I take any polynomial from zx, what happens to rf? That's the question, right? So tell me one thing. R is constant 2. Is it a polynomial?
Yes, sir.
What is RF? This is 2x plus 6, right?
Yes, sir.
Does it belongs to I?
Yes, sir.
Why? I. Oh,
Constant is
oh, it's a
multiple.
multiple of 3. Oh, sorry, sorry. I misunderstood the question. Ah, it's my bad. Oh, then it is an ideal, right? Oh, sorry, sorry.
Yes, sir.
Thank you. This is the benefit of being attentive in the session. I mean, I that's why I ask everybody to give responses. Whenever I ask, I misunderstood the question as it the constant term is 3. It's not 3. It's multiple of 3. Okay, okay. Yeah, I mean this is the proof then, right? You take any f belongs to I, then what happens to pf, right? Okay, okay. We have to modify this thing. Yeah. Okay. So let an element f belongs to I, which means constant term is what? F0, right? F0 is a multiple of 3. So what happens? Let any element R if you take from Zx. What is RF at 0? See, the product is a this scalar product you define. Sorry, this what do I say? The product in the ring you define pointwise, right? In polynomial ring. So you can write it like this: R0 times F0, right? What is this? R0 will be something, some alpha, let's say, and F0 is some 3 times beta, right? Because it's a multiple. F was in I, so it is a multiple of 3. But this is again 3 times alpha beta, right? Again a multiple of 3, which implies RF belongs to I, which implies what do you say? I is an ideal, right? Is it correct now?
Yes, sir.
Yeah. Thank you so much. I made a mistake there. Yeah. Now A is done, B is done, C is done. Okay, let's go for the next one. D. Okay. Oh, there is no D. So now the next question. Question number 5. Is it? Question number 5. So let R be the set of all functions from 0, 1 to R such that f is continuous. So, I mean, collection of all continuous functions from 0, 1 to R, real valued continuous function on 0, 1. This is your ring. Now, define mapping phi from R to this is real numbers. Okay, there's a difference between this R and this R. This is real set of real numbers. This is set of all continuous functions on 0, 1 as phi of any element f is integral 0 to 1 ft dt. So, prove that phi is a group homomorphism but not ring homomorphism. Proof. Okay. So for defining this group homomorphism, we need the structure on R, right? R is set of all functions. So what is the addition? It's the pointwise addition. What is the multiplication? It's the pointwise multiplication, right? So suppose you take two elements f comma g belongs to R. Phi of f plus g is integral 0 to 1 f plus g at t dt. But you know what is this? This is integral 0 to 1. This is ft plus gt dt, and using the simple properties of integration, this is 0 to 1 ft dt to 0 to 1 gt dt. This is phi f plus this is phi g. Right? This implies phi is a group homomorphism. Is it a ring homomorphism? Right? For that I need phi of f dot g should be equals to phi f into phi g, right? This I want. So is it true? Any guesses or any direction on how to proceed? This is an interactive session, right? We can communicate. Okay. So basically integral of product, is it same as product of integrals? Okay, so let's take f as, let's say something like this. Okay, this is 0, this is 1, and suppose I define 1 mapping like this. This is the line, right? This point is half, let's say. So what is phi f? Huh? So you can see, no, somehow this is like positive negative parts of this is not, in some sense it's an even function, it's an odd function, right? Around half, right? And half is your midpoint of 0 1. So phi f will be 0, right? But what, and if I take now g as I don't know, maybe, or what if I take g as g same as f only, right? And what is g squared? So what is g into f, or fg is simply f squared, right? So basically you have something like this, all positive map, right? Which implies phi of fg is non-zero because it's a positive function and integral is on positive domain, right? 0 1. It means the integral is non-zero, but when you take phi f dot phi g, you get 0, right? So I'll leave this rest of the calculations for you, because I gave the idea. You take the f as a function which is odd around half, so the integral will be 0. But then if you multiply it to itself, the integral will be positive, right? Non-zero function. See, this is non-zero function greater or equal to 0, so integral has to be positive, right? Is it clear? Question number 5. There's nothing remaining, right? This is just a line you can consider. This is like simply f of x equals to what can I say, x minus 1, right? Not x minus 1, some problem, it's half. Okay, so x minus half, so it's 0 at half, right? Yeah, perfect. This is the line, that's all. Its integral is 0 around 0 1. If I take the integral, I take x squared minus x by 2 0 1, right? So 1 by 2 minus 1 by 2 0. Okay, simple enough, you can easily do the calculations. There's nothing left anyway. So now question number 6. Yeah. So now question number 6 is regarding the power set of any set X. Let X be any non-empty set see if X has finite, if suppose the cardinality of X is finite, I mean X is finite, then what can you say about the cardinality of power set of X? Does anyone have any idea? The question is, I'll write in the red right now. If X is finite set such that cardinality of X is n, then what is cardinality of power set of X?
2 power n.
2 power n, right? Good. So how do you get this, right? So that I'll answer now. This was just the motivation for this question. So the actual question is, now if you consider the ring R as set of all functions from X to Z2, okay, Z2, okay, Z2 is just the ring of 0, 1, under addition modulo 2 and multiplication modulo 2. So if you consider all set of all functions, this is a ring, right? This forms a ring. Then you define a mapping of phi from power set of X to this ring R as phi of any element A. Now A is a subset of subset of X, goes to is defined. Okay. How is it defined? Phi of A has to be mapping, right? I should write it like this. Phi A, right? Phi A belongs to R, that is phi A for any element X is 1 if X belongs to A and 0 if X doesn't belongs to A. Right? What is this? Simply it's a characteristic function, right? Simply phi A is characteristic function. Right? You can also denote phi A as something like this, characteristic of A. Okay. So prove that phi is an isomorphism. Okay. So suppose we prove this, if phi is an isomorphism, then how can you directly get the answer for the above read question? See, what is the cardinality of f here, right? Set of all functions from set x to z2. Here your cardinality 2, right? So set of all functions from a set of cardinality n to a set of cardinality 2 is 2 power n, right? You know that. So from there you get set of what is the, because R is isomorphic to power set of x, say under this mapping phi, number of elements in R are same as number of elements in P over x. From there you can say number of elements in power set of x is 2 power n. So this extends the notion of finite cardinality. Even if you go for infinite set, suppose x is an natural number, then you can somehow say is px countable, uncountable. Same notion will work here because R will then have a cardinality 2 power c, right, where c is the continuum number, which is uncountable. Hence you can say power set of natural numbers is uncountable. Okay, so these are the motivation for this question. So how will we prove that phi is an isomorphism? Okay. Proof. Okay, so how is phi defined? Phi defined from power set of x to R as A goes to characteristic function of A, right? This is the map. Right? So let's take any two elements a comma b belongs to power set of x. What is happening with a plus b? So what is this? This is characteristic function of a plus b, right? And characteristic function at a plus b, the element x is 0. X belongs to a plus b, right? So, but what is this plus here? Yeah, plus is I should write this, not plus. Basically, if you are in power set of x, you have the symmetric difference, right? How do you denote this? This is a symmetric difference b, right? The triangle. 0 otherwise, right? Okay. And what is asymmetric difference b? It is a union b minus a intersection b. That's all. Okay. So if x, so what I want to prove right here, to prove characteristic function of a symmetric difference b is same as characteristic function of a. You are going you're going R, right? R, in R you have the function composition. Sorry, you have the component wise addition as the operation, right? So chi A, chi B, right? This you want to prove. Okay. So let's take. Okay, how to prove this? So if I take an element x belongs to a symmetric difference B, which implies x belongs to a union B, right? Minus a intersection B, which implies x is in a union B, which means x is either in A or x is either in B, right? Which implies chi A at x plus chi B at x, yeah, is 1, right? Because it is in A or in B, but not in both, right? Because you are subtracting the intersection, right? So x is A or B, but not in both. That means either this is 1, this is 0, or this is 0, this is 1, right? Something like this. So by adding you get 1, which is same as chi of asymmetric difference B at x, right? And if you, yes,
Yes.
yeah,
Yes, sir. Yes.
yeah, thank you. And now if you see the other condition, that is if x doesn't belongs to asymmetric difference B, okay, what does it mean? This means x doesn't belongs to A union B, right? Which means chi A of x is also 0, which is same as chi B of x is also 0, which implies chi A plus chi B at x is 0, which is same as chi of asymmetric difference B, right? Hence you are done. For every point x, you have these two functions are same, which means chi of asymmetric difference B is same as chi A plus chi B, right? So this is a group homomorphism right now. Next, you want to show that this is a ring homomorphism as well. Okay. So for ring homomorphism, what do you want? Phi of A intersection B, right? Here the product is intersection, right? You want this. What do we want? To be same as phi of A dot phi of B, right? Because there you have ring R, which is set of all functions, and there the product is the pointwise product, right? So what is this set? phi of A intersection B, which is a characteristic function of A intersection B. And that is phi A is characteristic function of A, phi B is characteristic function of B. Okay, so let x belongs to x. Okay. Yeah, so when is chi A dot chi B at x? What is this? This value is chi A of x dot chi B of x, right? So what these values can be? Yeah. See, this is the product, right? The product is non-zero if and only if both of the terms are non-zero, right? What are the conditions? Suppose if x is in only A and x is not in B, what do you get? Then you get this is 1, this is 0. The product is 0, right? If x is not in A and x is in B, then what do you get? You have this is 0, this is 1, right? But the product is again 0. And if x doesn't belongs to A and x doesn't belongs to B, then also you get 0 because both are 0. So the only case where you get 1 is when x belongs to A and x belongs to B, right? So whenever x belongs to A intersection B, it is 1. Every other case, x is 0, right? So I can write simply like this. Is 1 when x belongs to A intersection B and is 0 otherwise. But this is same as characteristic function of A intersection B. That's all, right? Then you have the product phi A intersection B is same as phi dot phi AB, right? See, look at these generalizations kind of thing, right? This is very abstract. How you deal with operations, yeah? I mean, naturally you look multiplication as kind of multiplication in your mind, right? But this is not multiplication. It is precisely the operation defined in your ring, whatever ring you are whatever ring is in the picture. Okay. So here I have proved that the mapping phi I defined is ring homomorphism. Okay. So phi, which implies phi is a ring homomorphism. Okay. Okay, now what was the question? I want you to show that phi is an isomorphism. Okay, okay. So I want to show it is bijective. How can I show now that the mapping phi is bijective? Anyone can try. I have showed that it's a ring homomorphism, right? I want to show that it's isomorphism, so it is enough to now the only part remaining is to show that the mapping phi is 1 1 and onto. So this is very easy now. You only have to show that phi is 1 1, right? We want to show that phi is 1 1. What does it mean? Suppose phi of A equals to phi of B. Then that means characteristic function of A is same as characteristic function of B, right? But when are these two functions same? See, naturally you can. It's very easy. This happens if and only if A is same as B. Okay, you can verify this is very easy verification. That means phi is 1 1. Now let f is an element in R, right? So now I want to show that phi is onto, so that every element in R has to should have a pre-image, right? So if f is an element in R, that is f is a mapping from x to z2, right? So naturally in z2 you have only two elements, right? 0 and 1, right? Something like this, 0 bar, 1 bar, right? So you look at the pre-images, right? Let you call A as f inverse of 0 bar. What does it mean? This is set of all points x belongs to capital X such that fx is 0 bar. I mean which maps to 0, and you map B okay. Yeah, you map B as f inverse of 1 bar, which is set of all x such that fx is 1. I want to show that f basically or something like this. If suppose I call f as f inverse of 1, okay, then what is a complement? Right? X belongs to a complement, which implies fx is not 1, but what the other possibility f has? Yeah? Fx has to be 0, right? That's the only case. Yeah, that means f is characteristic function of a, right? You take any element x, if it is in a, that means fx is 1. If it is not in a, it means fx is 0. That's all. Then no, which means this is phi of a. So every element has a pre-image, which means phi is onto. So phi is a one-to-one onto ring homomorphism, which means phi is isomorphism. Which means power set of x is isomorphic to R, which is set of all functions from x to z2. Any doubt in this question? Question number 6, you can ask. Okay, once repeat where you show homomorphism. Okay. Yeah, see. Under homomorphism, what do I have to show? Phi of a plus b in some sense. Plus is the operation of your power set of x. That is phi of asymmetric difference b should be same as phi x plus phi b. Right? So what is phi of asymmetric difference b? Okay. Is there any point? Yeah. So phi of asymmetric difference b here is what? Characteristic function of asymmetric difference b, right? Which is 1 if x is an asymmetric difference b, 0 otherwise. Right? So how do you conclude that the two functions are same when their images at every point it's same, right? So you take any point x in asymmetric difference b, that means x is in a or b but not in both. Right? This is basically the definition of asymmetric difference b. Then what happens for chi of x plus chi b of x? Right? So if it is in a, then it is not in b. So 1 plus 0. If it is in b but not in a, then 0 plus 1. Right? So in any case, you have 1. Right? They are not in both, so you don't have the case 1 plus 1. Correct. But this is same as chi asymmetric difference b at x. Right? So for every point in asymmetric difference b, the values are same. If it is not in asymmetric difference b, that means it is not in a union b. Right? I mean, not in A union B, or yeah, I missed one case. 1 minute. It is not in asymmetric difference B means it is not in A union B, or it is in A intersection B. Right? Yeah. This is the other case. But in both cases, see in this case, if x is not in A union B, you have simply this is 0, this is 0. In this case, if it is in both, then you have chi A is 1. Also, I mean chi B is 1. Right? And when you add, we have 1 plus 1, but in Z2 this is again 0, right? Which is same as chi asymmetric difference B. Okay? Yeah. Hariom, you wanted to point out this mistake, right?
Yes, sir.
Yeah, now is it fine?
So how can you write if X not belongs to in asymmetric difference B, then X not belongs to in A union B?
Or X is in intersection B. See, what is the definition of asymmetric difference B? This is A union B minus A intersection B, right? That means this is what set of all points which are in X belongs to A or X belongs to B, but not both. Right? This is simply definition of asymmetric difference B. So if I take an element which is not in asymmetric difference B, then what can you say? You say either it is not in A and not in B, or it is in both, right? Is it clear?
Sir, again repeat, please.
See, this is the analysis, a simple analysis. You have to analyze what this set has a definition. Asymmetric difference B means set of all points which are in A union B but not in intersection B. A intersection B. That means those points has to be individually in A or B, right? They are not in both. Okay. For example, I'll explain you by example. Okay, let's take A is, let's say, 1, 2, 3, 4. Okay, and B is, let's say, 2, 5, 6. Okay, then asymmetric difference B is, you get points which are in A union B. So 1 is here, 1 is not here, right? So 1. 2 is here, 2 is also here, right? So 2 is in the A intersection B, so you can't write 2. 2 is not there here, right? So you see 3 is here, but 3 is not here, so 3 is here. 4 is here, 4 is not here, so 4 is here. So 2 is there, I cannot write. 5, yeah, and 6, yes. So this is asymmetric difference B. So you take a union, right, and you don't write the common elements simply.
Sir,
Yeah.
where you write X not belongs to asymmetric difference B, this implies X doesn't belongs to A union B or X belongs to A intersection B.
Yes.
Then at right hand side, in two cases, either one of which, matlab,
Yeah, yeah. You can ask in Hindi also if you have some doubt.
can you understand Hindi?
Yeah, yeah, I can, I can.
सर इसमें राइट हैंड साइड में जो लिखा है एक्स बिलोंग्स टू ए यूनियन बी और ए एक्स बिलोंग्स टू ए इंटरसेक्शन बी, इसमें से कोई एक ही ट्रू हो सकता है ना?
हाँ.
तो अगर हम यहाँ पर लेते हैं कि एक्स नॉट बिलोंग्स टू ए यूनियन बी,
ओके.
तो ये केस कैसे पॉसिबल होगा?
मतलब ये दोनों में से कोई एक ट्रू हो सकता है ना. तो तुम पहले कैसे कर ले रहे हो, अगर एक ए दोनों में नहीं है, ए यूनियन बी में भी नहीं है, तब भी ठीक है ना. क्या दिक्कत है? मान लो अभी मैंने जो एग्जांपल दे रखा है यहाँ पे मेरा जो एक्स था, जो जो मेरा बड़ा कुछ सेट था, ए से लेके 1 से लेके 8 तक, उसमें से मैंने एक सबसेट लिया ए विच इज 1 to 4, एंड देन आई टूक अनदर सबसेट बी फ्रॉम 2 to 5 and 6. Then I can take my x to be, let's say, 8. Huh? 8 is not in asymmetric difference B, right? And one case is you can say x is not in A union B also, right? But on other side, if I take x equals to 2, right? This is there in the union. You can see it is there in the. Sorry, this is not in the asymmetric difference B. You can see, but this is in the intersection.
Yes sir, now it's clear, thank you.
Wait. No, I got your doubt. There is some technical mistake here. Yeah. So yeah, if it is there in the intersection, then it will be in the union, right? Of course, there is no. This is not the mutually exclusive case. Yeah. So how can I write this? If x is not in the asymmetric difference B, no, but these are the only two cases, right? I mean, X can be either an intersection or it's not there in the union. Yeah, no, these are the two cases. See, it's not like one does not imply the other. These two cases are not mutually exclusive, but these are the only cases you will get. Do you understand? Yeah, okay, good. Thank you. So with this example, you can refer. Okay, this example is enough for you to understand. This is an example. You take X this, you take A this, you take B. So any element which is not in the symmetric difference, you can say 8 is not in the union and this 2 is in the intersection. So those two elements are not there in the symmetric difference. Okay. So now let's go for the next question. We have question number 7. Okay. Let R and S be non-zero rings with unity and let phi from R to S be non-zero ring homomorphism. Then A, we have to show that phi of 1 R. Okay, this means this is the unity of R, ring R. So that if this is not same as unity of S, then this image of unity is a zero divisor. Okay, so basically see, there's a difference in maybe what you followed in the lectures. In your lectures, sir might have told that image of a unity has to be a unity, right? This is a case where you are in the integral domain, right? Where your codomain, this S has to be an integral domain. This is the part B. Part B says if S is an integral domain, then phi of 1R has to be same as 1S. And C, if this happens, if phi of unity goes to unity, then phi of every unit is a unit and this is the inverse. These are the three properties we have to prove. So A, suppose phi of 1 is not same as phi of 1s. Okay, how can I find, how can I show that this is a zero divisor? So I have to multiply, right, with something and show that it is a zero, so non-zero element. So this is not phi 1s, this is 1s. Okay. So basically what I can write phi 1r is phi of 1r dot 1r, right? Which is because it's a ring homomorphism, it is 1r dot 1r. So what I do is it. Anybody has any idea on how to prove this? okay, I can just write it here. Phi 1r minus phi 1r into phi 1r, right? This is 0, which is simply phi 1r times 1 identity here in S minus phi 1r. This is 0. Yeah, okay. So what I know is this is non-zero, right? Phi 1r is not same as 1s. This is non-zero, and this is also non-zero. I mean, if I take identity cannot go to 0, right? Then every element will go to 0. Okay. Yeah, it's not non-zero map, hence phi 1r is non-zero, and this is non-zero, which means, yeah, phi 1r is a zero divisor. Yeah, that's all. And in part B, see, if I'll label this as equation 1, let's say. If S is an integral domain, right, then from 1, you should conclude phi 1r equals to 0 or 1s minus phi 1r should be equals to 0, right? But this is not possible because phi is a non-zero map, and this is the case, right? What will you get from here? You get phi 1r is same as 1s. That means unity will go to unity. Okay? Yeah, so this is part B. What is part C? Yeah, if phi 1r goes to 1s, then image of a unit is also a unit. Yeah, this is simple. So you take part C. Let U belongs to R be a unit. Now, which implies U inverse is 1. What do you get here? You get phi of U inverse is same as phi of 1. Not 1, this is 1R. I mean, unity in the ring R, which is unity in the ring S. Because of ring homomorphism, you get this structure here. Yeah, so product of this element into phi u is identity, which implies what? Phi of u inverse is the inverse of phi u. That is what you wanted, right? So image of every unit is a unit, and you have this formula for the inverse. This is your C. So any doubt in this question? Question number 7?
No, sir.
Okay, thank you. So next is question number 8. Show that every ideal, let's say I, of ring Mn over R, okay, this R is any ring with unity, is equal to Mn over J for some ideal J of R. Okay, have you seen this question already? It is a very famous and very useful proposition. So how do you prove this? I mean, basically, if I take any ideal of Mn over R, it is simply set of all matrices with entries from another ideal J. This is basically the crust of the statement. How to prove this? So what I'll do is, I mean, first thing is I be an ideal, I be an ideal of Mn over R, set of all matrices. R is a ring with unity. So consider J as, what I want to do is, I have an ideal I, so there are matrices there. I will collect entries of each matrix in all of A. Okay, for every matrix A, I'll collect the entries of this matrix. Okay, how can you write this? See, if you have a matrix A, if I multiply this matrix A with EJ, EJ is a column vector with 1 at jth entry and everywhere else 0. So let's say I write this matrix A like this, A1, 1, A2, 1, something like this. Here I get A, 1J, A2J, something like this, AN1, ANJ, and like this, go on. Okay, ANN, sorry, A1N to ANN. If I multiply this with 0, 0, 1 at jth entry, all 0. This is jth entry. Then I get, if you do the calculation, I get the jth column. I get A1J, A2J, something like ANJ. Huh? And now if I do EI transpose AEJ, then I have multiplying this 0, sorry, 0, 0, 1 in ith entry, 0. This is ith entry. And here I have this column A1J, A2J, up to ANJ. So when I multiply, I get only AIJ, right? This ith entry multiply to this ith entry here, I get AIJ, right? So this is how I collect all the entries in all matrices of I. How do I write this? If I want to write the collection in a set form, I write like this: set of all EI transpose AEJ, where I comma j varies from 1 through n and a belongs to I. Okay, as I hope these notations are clear. Yes.
Yes, sir.
Yes, sir. Perfect. So this is my j. So my claim is this j is an ideal of R. So how can I prove this? See, whenever you want to prove something in a set, right, you want to see really what are the properties of the set. I mean, how is the set defined, right? So if I want to prove that J is an ideal of set, what do I want to do? Take any element from J, multiply with an element of R. I want to show that it is again of the same form. Correct. How can I do this? Yeah. So I want to prove that J is an ideal of R. Let you take an element, let's say A belongs to J, and an element R belongs to capital R. Right? What does it mean? A belongs to J implies A equals to some EI transpose A EJ, right? For some I comma j in 1 through n, and A belongs to I. I is an ideal of your ring Mn over R, right? Now if you do RA, how can I get RA similar, like by multiplying something to A? This is the thing. See, now consider matrix E. Okay, how can I do this? See, basically, if I multiply A with E, Kj, what do I get? Okay, what is this EKJ? Basically, it is a matrix. Okay, I should define this. EKJ is a matrix which has 1, and this is kth row and jth column. Everywhere else it has 0. Something like this. It's not in middle, but something like this. Okay. So if I do A, E, K, J, what do I get? First thing is you get a matrix which is 0 in the again jth column you have this row which is I write it like A K. Okay, this is everywhere 0. Okay, this is easy. This you can verify. Whenever I do A times EKJ, okay, I get kth column of A in the jth column position of the new matrix. Okay, and then if I multiply, okay, let's not confuse with J. Okay, let's say what do I do? Q times P times Q. If I do, then I have qth column here, and then I have pth row here. Then I will get, what do I get? In the qth column, pth, what do you say? Column of A. Yeah, this is the thing. And then if I multiply again with some A, E times Mn. Okay. Okay. So here you have a matrix with entry 1 in M in mth row and nth column. Here you have another matrix which has 0 everywhere except for what? The qth column. You have A raised to P. Okay, clear. What will be the multiplication? So all the columns except for qth column are 0. Or I can say something like this. So all rows, because when you are multiplying from left, it is easy to see from rows. Okay, this is like first row times first column, right? Second row times second column, something like this. So I'll for every other row you will get 0, right? Only at mth row you multiply it with qth column, right? So I'll get so in mth row I get the entry A, M, P, right? Ah. So is it? I mean, do you understand this? This is some heavy calculation, but I get this at what position? Nth row, qth column. So not MP, I get A NP. Yeah, because you are in the nth column, right? 1, 2, 3. You have to go that much there. So NP. Yeah. Okay. Good. So what I want is, I took an element A which is EI transpose A EJ, and now if I take an element R belongs to capital R, define a mapping, not define, so consider R times E, this is what is AIJ, no, this is IJ, the entry of this matrix A. if I take E1I, R times E1I, A times EJ1, something like this. Yeah. So what is this guy? Okay. So in this matrix, you have at ijth position, you get the entry R times A. Okay. At ijth position and 0 everywhere else. Right? You can see it from here. Okay. So now since A was in I, so this guy is in I, again this guy is in I. Okay, because I is an ideal, right? Since A belongs to ideal I, R E1I, A times EJ1 is in I again. And then what is R times A? You started with. This is simply inner product of what? Not inner product, simply EI transpose of this matrix here times EJ, right? Then done, which implies RA again belongs to J. So understand the mechanism, how I did. I started with any element from J, I multiplied it with any element of R. Then I showed that RA is also entry of a matrix from I. Okay. This is how we define J, right? So then I proved that J is indeed an ideal, right? Now I only have to prove that the ideal I is simply Mn over J. Okay. Is it clear? Any doubt if you have in this process, you can ask. Okay. The calculation stuff you can verify once. This is just matrix multiplication. Any doubt?
No, sir.
Okay. Okay. Now the only thing to show is I is equals to Mn over J. See, J is basically what? Collection of all entries of matrices in I, right? So one side is always true. Which side is always true? I is contained in Mn over J. This is always true. Okay. You want to show other way containment. Okay. Oh, it's heavy work. Let A belongs to Mn over J. Okay. How can you write? See, each entry, right? Each entry Aij is of this form, no? Something like EI transpose AEJ, right? Then you can verify. I mean, see, then you can simply verify that A is summation E ij summation Eij. So here also you have ij matrix. Okay, I mean for each entry you have another matrix, right? So Aij is some Ai transpose Aij of Ej. So I can do this. See, I'm basically using this formula here. Okay, but the only thing is the parameter stuff. Yeah. It is ijth entry, right? this is E L transpose from matrix A I J and then E L M. Okay. So I write A equals to E I L times A I J times E M J. Okay. And this L and M will depend on I and J. Okay. I mean, this is somehow conceptual. You have to understand really how L and M varies. Okay. It's not a variable kind of thing. For every I and J, there exists L and M for which this equation holds. Okay. So really the variables here are I and J. Because for each entry I and J, you have this thing. So I and J will vary from 1 to n. A can be written as summation of these matrices. Now it is simple since where each A I J belongs to ideal I. Okay. See, I is an ideal, hence this product is in I again, and then when you when you multiply this matrix with again EIL, again this will be in I, right? And this A will be summation of elements in I. Since I is a subring, this will again imply A is also in I. That's all. So you started with an element in M over J, you ended up in I. So M over J is again I, which implies I is basically M over J. Okay. See, this is really tricky. Okay, how do you write this combination? Okay, you have to really sit and do the multiplication. Really observe how the entries are relating. Yeah, and you refer this calculation above that we did. How I did E1I A EJ1, and then say this RA will be in not IJ. This will be in 1 1 position. Okay, this is 1 1 position. Okay, something like this. Okay, you have to really see the calculation, then the idea is clear. Okay, any doubt you have? Yes? If you have any doubt, you can ask. We can again do some clarifications. This is an important question. Okay, this problem will occur. Not in competitive exams, CSIR and GATE and all, but this is a question very important from the perspective of interviews. Okay, PhD interviews or anywhere if you want to go, they will ask this kind of question. Like, what are the ideals of Mn over R for any ring with unity R? So the answer is ideals are basically Mn over J for some ideal J. I hope this is clear. You can again rewatch the recording, and then if not, you will understand again. Okay. Next question is question number 9. Question number 9 says, let R be a ring with unity. Unity. Show that ideal, principal ideal generated by X. X is a polynomial, right, in Rx. X in Rx is maximal or is prime ideal if and only if R is an integral domain. How to prove this? Anyone has any ideas? So the only question is how does Rx quotient ideal generated by X looks like? See, we'll use the first isomorphism theorem. Okay, we can use that. Uh, yeah, we can use first isomorphism theorem and a theorem which says that an ideal is prime ideal. Yeah, perfect. It looks like R exactly. First isomorphism theorem and a theorem which says that an ideal is prime ideal if and only if R quotient I is an integral domain, right? First thing is consider mapping phi from Rx to R given as phi of any element polynomial can be written as P with as P at 0. Okay. What will you get here, right? P of 0 is simply the constant term of the polynomial, right? I mean, 0 is basically 0 of the ring R. Yeah. So then what is kernel F? Okay. Kernel phi are the polynomials with zero constant term, which is simply ideal generated by X, right? And show that, and it is easy to see that phi is onto R, right? Homomorphism, hence R is isomorphic to Rx quotient kernel X. So, ideal generated by X, right? So now you have a theorem that an ideal I is prime if and only if R quotient Rx quotient I is integral domain, right? Now you have the answer. When is this ideal prime ideal if and only if Rx quotient X, right? Which is same as saying R is integral domain. Yeah? You got an answer. Is there any doubt?
No, sir.
Yeah, and if I want to extend the same question, I'll ask when is ideal generated by X a maximal ideal? Yeah, the answer will be when R is a field. Yes?
Yes, sir.
Okay. Now we'll go for the one more question. So I have two questions more, but since there is no time, I'll just maybe say one proposition, and then the question based on the proposition I'll take in the next week. Okay. So the proposition. Tell me if this proposition is already known to you or not. Uh, let R be a ring with unity. Let me check. Do you need unity? Yeah, you need unity. Yeah, a ring with identity. Any then every proper ideal is contained. Let R be a ring with unity, then every proper ideal is contained in a maximal ideal. Okay, this is the proposition, and basically what is the question. I'll state the question also. You can try the question exercise. If not, I'll explain this in the next class. It's a very interesting question. Question is, you can use this proposition for this question. Okay, same RB ring with unity. Unity such that R has a unique maximal ideal, then show that for every x which belongs to R minus M, where this M is the unique maximal ideal. Okay, I'll refer this as M, is a unit. So like basically every element outside this maximal ideal is a unit. Okay, so I'll leave this as a exercise. You can use this proposition to solve this exercise. Is this proposition known to you? Is it already explained in the class lectures? Every proper ideal is contained in maximal ideal. Yes. Okay. If not, you can try for the proof also. This proposition can be proved using John's lemma. Okay. If not, I'll explain this in the next week. Okay. Now time is over, so I'll explain this proposition next week again, the proof and this exercise also. So if you have any doubt in session so far, you can ask.
No, sir.
Okay. Thank you. Thank you. Then if you have no doubts, you can leave the session. We'll meet next Thursday. Thank you.